We've seen in the past few lectures that the theoretical motivation and observational evidence for both stellar mass and supermassive black holes appear to be compelling. But it's still very hard to get an intuitive feeling for what black holes are like. Various scenarios have appeared in science fiction books and movies, and also in cartoons. One of the most popular episodes of Ren and Stimpy, for example, is Black Hole, where Ren and Stimpy get pulled into a black hole. Their bodies morph into weird shapes, various body parts come off and then reassemble. This actually does bear some resemblance to reality, but of course it's grossly inaccurate in many respects. Here we will explore what you would see and experience if you were traveling toward a black hole and then into it. We'll also discuss what a distant observer would see as someone falls toward a black hole. If you fall without any rocket power toward a black hole, to a first approximation, your entire body moves at the same rate. You're in free fall, like an astronaut in space, with everything following the same natural path through curved space-time, since the gravitational pull is roughly constant over the entire spacecraft. Balls and other objects just float along with you, not moving relative to you unless you give them a push. This is what gives rise to the feeling of weightlessness. You're falling and so is the balance on which you're standing. So in fact, you don't register any force on the spring and the balance. You feel weightless. But in fact, as you approach a black hole, gravity is no longer constant over the length or width of your body. You get stretched and squeezed by tidal forces, especially in the case of a low-mass black hole. Now, these are qualitatively similar to the reason that there are tides here on Earth, due to the differential pull of the moon. The moon pulls on the near side of the Earth more than on the center, pulling the water toward it, and it pulls on the center of the Earth more than on the far side, so effectively the water is pulled away from the center of the Earth on the far side. In a diagram like this, if you're near a stellar mass black hole, your feet are significantly closer to the center of the black hole than your head is. If you have a height of 2 meters and the Schwarzschild radius is 30 kilometers, well, 2 meters is actually a significant fraction of 30 kilometers. So your feet are being pulled more than your head. You're being stretched in the vertical direction. Your shoulders and sides are also coming together. They're being squeezed because all of these arrows point toward the center of the black hole. So you get stretched and squeezed. This process is informally known as spaghettification, even among physicists and astronomers. Well, there's this joke, that my wife Noelle and my father-in-law Gary came up with. So how do black holes like to eat? They want everything spaghettified. Well, that's stretching it a bit. But really, if you fall from rest, you start out slow and then you go pasta. I like corny jokes like this. My wife does as well. Anyway, when I give my lectures at Berkeley, at Cal, there's one day when I dress up as a black hole. It's Halloween day or the day next to it. And so I'm the black hole. I kind of look like the Unabomber. And this thing around my neck is a little toy alien. I brought it with me here. It says, how do you like that? Let me do it again. Okay, so the black hole is falling into, the alien is falling into the black hole and being spaghettified, tidally stretched. It's a real hit among the students. So don't get too close to a low-mass black hole, or you will certainly be ripped apart. Now, an example of this is one process by which we think short-duration gamma-ray bursts occur. If a neutron star is close to a black hole, it gets ripped apart tidally when it gets closer and closer, and then that feeds into the black hole and somehow, through a process that's still a bit mysterious, produces this pair of outflowing jets. Compared with a low-mass black hole, however, a supermassive black hole has a much larger event horizon from which you cannot escape. So in a sense, a supermassive black hole is more dangerous because it's a bigger thing, but in terms of tidal forces, it's less dangerous. A supermassive black hole that's, say, 3 billion solar masses has a Schwarzschild radius of 9 billion kilometers. My 2-meter height compared to 9 billion kilometers is a much smaller fraction than my 2-meter height compared to 30 kilometers. So the difference in forces is much less. The pull on my feet is only a little bit greater than the pull on my head in that particular case. So I don't get spaghettified outside a supermassive black hole. You don't get spaghettified until you're pretty close to the singularity, in fact. So a supermassive black hole like that in M87, 3 billion solar masses, would be relatively safe to study from a close distance. Well, for something the size of a star, even a supermassive black hole would be a dangerous place because the force on the near side of the star is greater than the force on the far side. Stars get tidally disrupted by supermassive black holes unless those black holes have a mass greater than about 100 million solar masses. Then even a star won't get disrupted. Part of the disrupted material goes into the black hole, and part of it stays on the outside, accretes, and emits light. So you might expect flares from the centers of galaxies that are tidally disrupting stars. And indeed, when we look at some galaxies, they look pretty normal for a while. We circle the nucleus there. But then at X-ray wavelengths, suddenly this particular one flared up, became very bright. We think this was the tidal disruption of a star that came very close to this supermassive black hole. So you can see an animation of what the star might look like. It's just sort of cruising around. But it's losing energy because it's drifting through gas and dust, and that exerts some friction. When it gets close enough, it gets tidally disrupted. And this process also, by the way, should emit gravitational waves. So there should be a gravitational wave signature of such events. You then see the accretion disk. Stuff is falling in, and it heats up, and it emits an X-ray flare as it heats up, causing a mildly active galactic nucleus for a short time. This kind of behavior, we think, has also been seen in the ultraviolet with the Hubble Space Telescope. In some cases, in fact, the tidally disrupted star can contribute to a greater outflow in the relativistic jet that seems to emanate from a lot of active galaxies and quasars. So here's an animation of the star being disrupted, gradually being accreted onto the supermassive black hole, and then as the gas gets very close in, it creates this jet, contributing to either an existing jet or creating a new jet of its own. Well, suppose you could travel safely toward a black hole. You would see a highly distorted view of the sky because of the strong gravitational field, the strong curvature of space-time. This leads to an effect known as gravitational lensing. For example, if you have a galaxy whose light is passing next to an intervening cluster consisting of visible and dark matter, that intervening cluster bends the light of the background galaxy, creating arcs of light, gravitational lensing. Basically, the background galaxies have been stretched out into these arc-like shapes. And in this famous picture, there are many cases of background galaxies being stretched into arcs by the mass of this foreground cluster and the phenomenon of gravitational lensing. You can even get what's called an Einstein ring if you get a very symmetric configuration. The foreground object, the background object, and the Earth are perfectly collinear and spherical. Then you get an Einstein ring. Here's a simulation of what one might see if a black hole reasonably close to us were passing between us and a bunch of background galaxies. The light from those galaxies would be gravitationally lensed, and there you see an Einstein ring. But look at that stretching. It's just this weird gravitational distortion. You're seeing the effects of the curvature of space and time. Here's an animation of what the Earth would look like orbiting a black hole at a radius of 3 Schwarzschild radii and viewed from a distance of 5 Schwarzschild radii. Look at those wild distortions of the Earth. Wow. Okay, so let's travel toward a non-rotating so-called Schwarzschild black hole. Let's choose a supermassive one, like in the middle of a big galaxy, so tidal effects are much smaller and you don't have to worry until you get close to the singularity. Exactly what you would see depends on your speed, whether you're in free fall or slower, like if you have rockets firing or whatever. We're going to do a few examples, but mostly free fall. Now, Robert Nemiroff at Michigan Tech has a nice website where he shows what one would see if one were falling toward a black hole. And the first thing you notice is that most of the stars get split into two images or even these little arc-like structures. Here in this still from one of his animations, you can see a view of the sky toward the constellations Orion and Canis Major, the Great Dog. And for example, Sirius, the brightest star in the sky, looks bright but also has a fainter counterpart opposite the black hole. And the constellation Orion also has a counterpart. So let's look at one of these animations. You're falling toward the black hole and the black circle grows. Stars around it are getting pushed outward by the gravitational lensing effect, and you see double images. Now, if you get to a radius of 10 Schwarzschild radii and you decide to circle the black hole, then large light bending effects are seen, causing the background sky to appear to move in really unusual ways as you circle this black hole. The light paths are so curved that you see all these weird effects of the stars going around in clockwise and counterclockwise directions depending on how close their light passes to the event horizon of the black hole. A very weird sight. Another great website was constructed by Andrew Hamilton at the University of Colorado. He took the equations of general relativity and tried to simulate what you would see falling into a black hole in a very realistic way. Now, again, he ignored tidal effects for a while. He chose a supermassive black hole so that you don't have to worry about them for a while. But in many other ways, his calculations are extremely realistic. And I encourage you to go to his websites and explore his various animations where he shows what happens as you're falling in toward a black hole. And the website is continually being improved. It's really a fantastic website. Well, the animations are computed using general relativity, and you're falling into, in his case, the center of the supermassive black hole in the Milky Way galaxy. His computations were done using an assumed mass of 5 million solar masses for the supermassive black hole in the middle of our Milky Way. The true mass is probably 4 to 4.5, so you have to adjust the times a little bit, but that's just a quantitative change. Qualitatively, there's no real difference. The background for his animations is Axel Mellinger's beautiful Milky Way panorama, made from a whole bunch of photographs stitched together. These represent an optical view of our Milky Way galaxy, and the red plus sign shows you where the supermassive black hole is located. It's a beautiful picture. In the animations, there's a map of the freefall trajectory that you take. Now, the green annulus is the region where there are stable circular orbits. The yellow annulus represents unstable circular orbits. In the orange region, there are no circular orbits unless you fire your rockets in the appropriate way. And then the red circle is the event horizon, and the red color is inside the event horizon. You'd get turned into a bloody mess eventually inside there. There's also a clock that tells you the time in seconds measured on your watch from the horizon to the singularity. So in the case of the supermassive black hole in the middle of our galaxy, he computes 16 seconds. Using the smaller mass, it would probably be more like 13 seconds, 13 or 14 seconds. But again, these are just minor quantitative differences. The qualitative effects are accurate in these animations. He paints a red grid on the black hole's event horizon. Now, of course, there won't be such a grid in reality, but to see the distortions of space, it's useful to have such a grid painted on it in the computer animations. You notice here that you can see both the north and south poles of the event horizon simultaneously. The black hole's gravity, or curvature of space, bends light around it so much that you can effectively see the backside of the black hole. What a wonderful thing. All right, well, here's the same picture, but without the red grid. You see it looks a little bit more boring, but there's a nice Einstein ring in the background there. Let's now fall freely toward this black hole. Look at the distortions that you would see in the background starlight. The event horizon is getting bigger and bigger as you approach, bigger in angular size. You now see the coordinate grid. Now you enter the region where unstable orbits exist. And then closer and closer as you see this grid coming upon you, the two poles of the black hole are now quite close together. You're getting very close to the event horizon now, and boom, you've reached the event horizon. You now see two coordinate grids because effectively you see two event horizons after you enter the black hole. I'll explain more why that is in the next lecture, but it's a cool effect. Let's view this again, but this time without the map and especially without the grid. You'll notice that in fact, though the effects appear the same as with the grid, they're a little bit easier to see because you don't have all these other lines in the way. On the other hand, without the grid, you also can't tell when you pass through the event horizon. And this really emphasizes the point that the event horizon is not some place where there's a huge amount of matter and weird things happen. It's just a place beyond which you can't return. But nothing obvious happened. The obvious thing happens there when you hit the singularity, but I think you couldn't really tell when you were hitting the event or passing through the event horizon without the coordinate grid, right? It's just a point beyond which you can't return. So it's definitely an eventful place, but there's nothing much going on there. You don't get squeezed or shredded or anything like that. Well, how's that for a wild ride? I think, it looked pretty neat. But let's dissect it so we can explore the various parts in more detail. Here's a still showing the Einstein ring when a bright object is directly behind the black hole. That's a beautiful Einstein ring. There is what you see when you're at a position where you would have the innermost stable orbit. This occurs at a radius of 3 Schwarzschild radii for a non-rotating black hole. Within 3 Schwarzschild radii, you can no longer have stable orbits unless you fire your thrusters. There's the same view, but without the coordinate grid. Now let's go to a region 2 Schwarzschild radii away. That's a region where you could have an unstable circular orbit. A small deviation of your rocket ship will send you either into the black hole or out into space. In the distant future, when our descendants perhaps visit the supermassive black hole in the middle of our galaxy, surely they will want to stop along the way a little bit and get a tour, right? You don't want to just freely fall in. That's a pretty short-lived trip, and you don't get enough time to really see what's going on. So let's suppose you put yourself on a stable orbit at 2 Schwarzschild radii and circled around the black hole. What would you actually see? Well, you'd have about 10 minutes to orbit the black hole, and you'd see the coordinate grid changing underneath you and all these stars flying past in the background. It would be a wonderful sight. Let's now go back to the freefall animation. Although at the photon sphere, photons in principle can get stuck in circular orbits, in practice, the photon orbits are unstable and either go zipping into the black hole or back out into space. Nevertheless, at the photon sphere, this is what you would see. There's with the coordinate grid and then without the coordinate grid. This is the closest to the black hole that anything can remain in a circular orbit without firing its rockets. Nemerov, going back to his animations, shows that at the photon sphere, no light emitted outside can reach you from below. You look down into the vast emptiness of the black hole. The sky you once knew is now behind you, compacted to occupy only half of its original area. So let's look at this thing. Whoa, it's just growing, and the sky behind you is where you see the stars. But down below, all you see is this vast darkness. Now, suppose you're a tourist and you want to orbit at or near the photon sphere. You'd have to travel at the speed of light, and that's not possible because it would take infinite energy to do so. But you could go almost at the speed of light if you had enough energy. Let's see what you would view if you were orbiting at or near the photon sphere. You'd see all these stars zooming past, being distorted, and then zipping outward along radial paths. Wow, look at that. Boom, boom, all these stars zipping by. Now, Hamilton's version includes redshifts and blue shifts because as these stars are moving toward you and away from you, they will either be blue shifted or red shifted. Let's see his version. Look at that. Isn't that fantastic? Whoa, it's so wild. That would be so much fun. There it is with the coordinate grid. Let's show it again with the coordinate grid. What a wild ride that would be. So that's at or near the photon sphere if you were traveling nearly at the speed of light. Now, if you lower yourself very slowly toward the horizon, that is, you take yourself out of free fall, and you fire your rockets like crazy just to stay put, okay, then it turns out your view of the outside universe will be concentrated into a small bright circle just above you. The universe looks brighter and brighter as you slowly approach the horizon, tending toward infinite brightness, but in a smaller and smaller patch. Let's look at what you would see. There you are. You're looking outward at the universe, and it goes to infinite brightness. Boom, look at that, as you reach the horizon. So you're not engulfed in darkness right away. If you're looking in the opposite direction out of the black hole, you actually see the whole universe being crammed into a smaller and smaller area, tending toward infinite brightness in a flash at the end. What fun that would be. Well, let's go back now to the free fall animation. Okay, we've stopped our little tour at the photon sphere and at the event horizon. Let's go back into free fall now. When you cross the event horizon, the coordinate grid splits into two. You actually see two horizons. It's really weird. Without the coordinate grid, however, you can see that, in fact, nothing special is visible at the moment that you cross the horizon. It doesn't look qualitatively different from a few moments before crossing the horizon or a few moments later. But the coordinate grid splits into two. That's how you know you've crossed the horizon. Then you are pulled inexorably inward. There's nothing stopping you at this point. You still see the two coordinate grids. They look highly distorted. Without the coordinate grids, again, that looks qualitatively not different very much from what you saw a few seconds ago. The tidal forces start pulling you apart as you get sufficiently close to the singularity. You know, you get stretched lengthwise and squeezed along your width. What a way to slim down, you know. However, like many diets, this improvement to your shape would be only temporary. You'd get stretched apart, spaghettified, torn into shreds. It would not be fun. Here's what the situation looks like without the coordinate grid. Again, more boring looking. To the singularity we dive. Oh boy, the coordinate grids now come together in these loops. And then when you hit the singularity, zap, all the loops come together, and then you just have darkness. It envelops you. If you were alive and cognizant of what was going on, you'd see at that point darkness envelop you. But really, everything at that point would be squished into the singularity, so no brain cells or thoughts could exist. Here's the view at the singularity. Total darkness. Without the map and the clock, just a black screen. Well, I promised you a wild ride in this lecture, didn't I? I think I delivered. What a wild ride. Now, suppose you want to throw your mortal enemy toward a black hole. So you're pretty far from the black hole, and you know what'll happen because you've done all these theoretical calculations, but you still hate this alien or whatever it is, and you throw him in. Suppose you're Luke Skywalker, and you're saying to Darth Vader, "Die, you wicked fiend." But Darth is saying, "But Luke, I'm your father." And you say, "Well, tough, you know, I'm going to throw you in anyway because of all the things you've done." Well, what would Luke see? Luke would see Darth Vader's clock slow down due to gravitational time dilation. Go back to this diagram here. If you've got a clock near a black hole and a clock farther away, and they are initially synchronized, then if, say, 4 hours pass on the clock far from the black hole, only 2 hours might have passed on the clock close to the black hole. As seen by the outside distant observer, the clocks of the infalling observer slow down. Now, the infalling person, Darth Vader, doesn't realize that the clocks are slowing down. In their own reference frame, objects that are falling in don't even really know that they're falling in unless they're being tidally stretched apart. But from the perspective of the person outside, time slows down. And in fact, to Luke, it would appear that Vader never falls in. Time comes to a halt as seen from Luke's perspective when Vader reaches the horizon. Indeed, nothing ever falls into a black hole from the perspective of outside observers, because once the particles reach the event horizon, the time dilation becomes infinite. Time stands still. Well, now you can see why some physicists and astronomers referred to black holes as frozen stars some decades ago. A star collapsing to form a black hole is never actually seen to cross the event horizon. It just keeps falling more and time slows down, and it becomes frozen as a little envelope, a little membrane, just infinitesimally above the event horizon. Now, the term black hole was coined by John Wheeler in 1967 because it was just more visually descriptive of what a black hole really is. Frozen star just didn't grab people's attention. And the other term that was used a lot, continuing collapse, just didn't grab people. But he said, hey, it looks black at that point because even though the stuff never crosses the horizon, it actually does fade from view because fewer and fewer light rays reach you. Most of them get caught within the black hole. And those that do reach you are so incredibly gravitationally redshifted that visible light has become infrared or radio waves or whatever. So in fact, though the star is falling in and doesn't cross the horizon from the outside viewer's perspective, it does in fact fade from view because few of the photons actually reach you, and those that do are gravitationally redshifted. Now, from Vader's perspective, he definitely does fall in. He crosses the event horizon after a finite time and then hits the singularity a finite time later. Indeed, the total maximum time to live is given by the formula pi g m of the black hole, the mass, over the cube of the speed of light. And when you put all those numbers in, it turns out that the maximum time to live, if you were to cross the event horizon of the supermassive black hole in the middle of our galaxy, would be only 1 minute. 1 minute to live if you fire your rockets in the appropriate way. Most trajectories give you even less time to live. So, you don't have long to explore the innards of even a supermassive black hole having 4 million solar masses. Now, if you took one that had 4 billion solar masses, that would give you 1,000 minutes to live. You could write a little essay about your experience in that amount of time, like the one in the middle of M87, But you definitely can't just park yourself inside the event horizon and expect to stay there. You'll hit the singularity for sure no matter what you do. So don't park on that side of the event horizon. All right, well, suppose Vader is falling in, but he turns on his rockets, and before crossing the event horizon, he has so much thrust that he can actually stop himself from falling in and then come back to fight Luke again. You find in that case that Vader will have aged much less than Luke did, because Vader spent a long time near the horizon where clocks were running slowly. All clocks, physical clocks, biological clocks. This refers to any method for keeping time. Vader aged less than Luke did. So he will come back to face Luke, who's now, old and weak perhaps, and Vader will still be strong and, able to fight. This is a way of jumping into the future without aging very much. You can't read more books or anything like that because you don't spend much time on your own clock's frame of reference near the horizon, but you have jumped into the future relative to the people who stayed at home, okay? Anyway, it's a wild thing to do. You wouldn't really want to send any of your friends or enemies, I think, to such a horrible death, but this is what would happen if you really were to do it. And we think we've seen some observational evidence of gas falling in showing some of these effects. Here, in the case of Cygnus X1, there's an accretion disk and a blob falling in. It gradually fades from view and becomes gravitationally redshifted as it gets closer and closer to the event horizon. Moreover, if there were a clock, we would see it slowing down. But there, it faded from view and became redshifted. But you didn't actually see it cross the event horizon. Now, if that blob were Darth Vader, he would see blue-shifted, high-energy light from Luke and the rest of the outside world. This would be gravitational blue shifting, the opposite of gravitational red shifting. Well, falling into a non-rotating black hole is certainly a wild ride, but you'd be doomed to hit the singularity. It would be better to hover for a while just above the event horizon, soaking in the view. In that case, you could come back to Earth far in the future, not having aged much. This would be a way of seeing the future, but you could not go back to your loved ones. Now, in some science fiction books and movies, there is travel through a black hole to a distant part of the universe, or even to another universe. Sometimes people even seem to go backwards in time. In the next lecture, we'll explore whether this is indeed possible.